In this question, we want to determine algebraically whether the functions are inverses of each other. So the way that you would do that is you would take one of the equations. So in part I, if I take the first equation, y equals 3x minus 6, and I want to find out algebraically what the inverse is, that's where we switch the x and the y and solve for y. So add 6 to both sides, divide by 3, and whatever we get in the end, and we might have to simplify or rearrange things, but you want to check, is that the same as the other equation? So we got y equals x plus 6 divided by 3. They suggested y equals x minus 6 divided by 3. Do they match? No. So they are not inverses of each other. For the second one, here we've got a parabola and we've got a restricted domain. So we've seen these restricted domain things this morning. It's only going to be half of the parabola. Now I'm going to show you some other things that come up interesting with the restricted domain and how it might be able to help you decide which equation you have and which graph you're going to have. So first of all, if we switch x and y, you're going to get x equals negative y squared plus 3. But you can also switch x and y with domain, because with inverses, the domain becomes the range, and the range becomes the domain. So if x was greater than 0 before, when you switch the x and the y, now y has to be greater than or equal to 0. So a little bit of rearranging. I'm going to subtract the 3 on the other side. Ooh, actually, are you okay if I do this? Because there's a negative with that y squared, I'm going to move the y squared to the left side and move the x to the right side. And then we can square root it right away. And remember, when you square root it, you have to include the plus or minus. But because y is greater than or equal to 0, that means your y values go up. Can you see from that, if you're thinking about a square root, one square root goes up and one square root goes down? Can you see just from this little idea of switching the x and the y, it has to be the positive one. Now, does that match? Yes. I mean, they have 3 minus x, we have negative x plus 3. But that is the same thing, so we can say, yes, they are inverses of each other. Now, in part B, it says verify the answers to part A graphically. So how would you verify something graphically? Well, what we're going to do is we're going to graph one equation in green and the other equation I'll graph in red. So we'll put both graphs on the same graph. We'll do one in green and one in red. So here is the first one. We had y equals 3x minus 6. So for the original graph, we would have a y-intercept of minus 6 and a slope of 3. So 1, 2, 3, up 3 over 1. And there would be our graph. For our second one, for the red graph, I'll just label this one. For our second one, we've got x plus 6 divided by 3. Well, not our inverse, but our original one was x minus 6 all divided by 3. Well, this isn't in y equals mx plus b form, so we have to do a little bit of algebra just to rearrange it, just to make it work. When you're dividing a numerator by 3, that means each of those things is divided by 3. The x is divided by 3 and the negative 6 is divided by 3. And we can write x divided by 3 as 1/3 times x, because that's the same thing as x divided by 3, and then minus 2 instead of minus 6 over 3. That tells us that we now have a y-intercept of minus 2, and a slope of 1/3 means you go up 1 over 3, and this is our graph. Now, graphically, how can we tell that those are not inverses graphically just by looking at them? Well, you're going to use the idea that an inverse is a reflection over that line y equals x. So a couple of things need to happen for that to be true. One, if it is true, there should have been a point right here where the green graph would have crossed that line, because anything on the line y equals x is going to stay the same. So that's one reason right away that I can tell that these are not inverses of each other. I mean, you could draw the actual inverse one. The actual inverse of the green graph should be that line. Can you see that that line is a reflection of the one line over y equals x? The purple one here reflects over the line to get the green one. And so the red and the green are not inverses of each other. Just going to move this over here to be closer to that line. For the second one, our original graph was negative x squared plus 3. So if you think about the negative, that's going to flip it over the x-axis and then shift it up 3. So we're going to have a parabola that's down and shifted up 3. And does it make sense that we're only going to have this half for our green graph, because the domain is restricted to be x is bigger than or equal to 0. Graphically, if you want to graph the other graph, this is a great example of how we could do something simple to make life harder on you. You might look at that and say, oh, I don't know how to do that, because it's 3 minus x, and it looks weird. Well, rearrange it into a form that's more comfortable for you, right? We usually have the x first and the numbers afterwards, right? So we can first of all, we could rearrange that to be negative x plus 3. What will that negative do? It's a horizontal reflection, right? It's going to reflect it over the y-axis. What's the 3 going to do? Some say left 3, some say right 3. Okay. What was the special note that we wrote down a couple days ago? That dumb special note, eh? Yes. Whenever you have a horizontal reflection, stretch or compression, and a horizontal translation, you always have to factor first. So that would come out, and you'll have x minus 3, so it is 3 to the right. So imagine your square root graph flipped over this way and then moved 3 to the right. So you'll have this point going in that direction. If we look at the diagonal line, this one does show that they're inverses because they share this common point. You can look at specific points like 0, 3 changed and became 3, 0. So we do have the x and the y switching with each other. All right, 7, 8, 11, and 13. And 11 and 13 are designed to make you think. Yay.